Periodic Properties 3. This video will cover the periodic properties, electron affinity, and electronegativity. Electron affinity is defined as the energy released when an electron is added to a neutral atom. When an electron is added to a neutral atom, we get a 1- ion. The electron is added to the lowest energy, unfilled orbital. As with ionization energy, it is possible to add more than one electron, but we will focus only on the first addition. Here are the main group elements, the tall columns, for the first 5 periods of the periodic table. What kind of patterns do we see here? First of all, although it is far from regular, the electron affinity seems to increase as we go across the period from left to right. We will talk about exceptions later. In the columns, the electron affinity seems to increase going up a column, though again there are exceptions. These general trends make sense, since the trend in a row depends on the pull of the nucleus for the added electron, and the nucleus gets larger and more positive as we go to the right. In a column, the energy would depend on the energy level to which we are adding the electron. The energy level increases as we go down a column. So as we come down a column, the electron does not get as close to the nucleus and gives off less energy when added. These are the same patterns and reasons that we had for ionization energy. As with ionization energy, there are exceptions to the general patterns. This time, however, there are 3 of them. The noble gases all have electron affinities greater than 0, which means that we have to put energy in to add an electron, rather than getting energy out. Why? The noble gases have a filled valence shell, S2p6, and there is no room in the valence shell for any more electrons. So the electron would need to go into the next shell. The energy of that shell is significantly higher than the energy of the valence shell, so the electron does not give off energy when it is added. Group 2. Group 2 is also an exception. Group 2 elements have a configuration of S2, so the next electron would need to go into a higher energy subshell, the p subshell for beryllium and magnesium, and the D subshell for calcium and strontium. The subshell is not as much higher in energy as the next shell is, and the D subshell is not as much higher as the P subshell is, but putting the electron in the higher energy subshell would still release less energy. Group 15 elements have a P3 configuration, which is 1 electron in each of the p orbitals. The next electron would have to pair up with one of the other electrons, which causes electron repulsions, which decreases the energy released. Notice that, since the repulsions decrease as the orbitals get larger, the lessening of this exception as we go down the column is not unexpected. It probably also explains why the column as a whole reverses the pattern of increasing as we go up the column. So, the general trends for electron affinity are the same as for ionization energy. Electron affinities increase as we go across a period to the right, and as we go up a column. We should exclude the noble gases from this because they are a big exception to the pattern. And the other exceptions are groups 2 and 15. Again, the exceptions are for members of the group and the element immediately preceding the element in the row. Electronegativity. Electronegativity is defined as the ability to attract electrons in a bond. That means the element is not only attracting its own electrons, but also the electrons of another atom. The property related to attracting its own electron is ionization energy. The property related to attracting another atom's electron is electron affinity. So we should expect that the electronegativity would vary like those two properties do. So, when we look at this table of electronegativities, we should not be surprised that the electronegativity increases as we go across a period from left to right and increases as we go up a column. Once again, there are many exceptions, but there does not seem to be a pattern to them.